So, on the agenda today, so Wednesday I went through this extra fast Kaufman bracket, and I hope you followed because I went through it extra fast. And but I want to clarify it a little bit today by putting it into some algebraic context. And second thing on the agenda is to talk about worms in apples. So I hope you all know the joke, right? What's worse than a worm in an apple? Anybody knows?
A worm?
Half a worm.
A worm.
Half a worm.
A worm, what's worse than a worm in an apple? Oh, half a worm in half an apple, right, good. So, you'll see, I'm sorry, you'll see in a minute why it's relevant. And the last thing is on beyond zebra. So, you know, I hope many of you, at least those of you who grew up in North American cultures, know Dr. Seuss, and one of their books is On Beyond Zebra. So it's an alphabet book. So like there is apples through zebra in all alphabet books, and they go beyond zebra. So there is a letter Uz to describe I forgot what, and a letter Wam, and a letter and a letter Humph, and a letter Fuddle, and so on. And the way this is relevant for this class is it turns out that, okay, so when you go through algebra, you go through groups and rings and fields and modules, I don't know, maybe a couple of other things, and you tend to get this feeling that all of mathematics is about studying these several A to Z objects. But in fact there are plenty of algebraic structures that aren't groups or rings or fields and that are equally interesting. So today we'll see one of them, a planar algebra. But later in the class we will see canopolis and quandles and various other kind of things beyond zebra. Okay? So sorry, so this is the introduction to the introduction, and really what I want, the two main theorems I want to show today are saying the following. So the following is, the first one is that the Kaufman bracket is a morphism from the planar algebra of tangles to the, sorry, I misspelled, so to the temporally, I think that's how it's spelled, Lieb planar algebra. And the second theorem that I will want to show today is that the rank over the Laurent polynomials in a variable a, so the rank over z adjoined a plus or minus 1 of the temporally Lieb algebra at level 2n is equal to the so-called nth Catalan number, which is equal to 1 over n plus 1 times 2n choose on n, which is approximately 4 to the n divided by n to the 3/2 times the square root of pi, and you'll see why these two theorems are a formalization of what we said last time. Okay? So, but let's start from kind of the worms and apples and planar algebras. So the idea is that you have a complicated knot. Again, here is our complicated knot. And in order to compute its Kaufman bracket, you have to, so suppose it has 100 crossings, you have to do 2 to the 100 operations. But now, if I had a half knot, so suppose I cut it in half. So instead of a worm in an apple, on each side I'd have half a worm in half an apple. Okay? So, I'm sorry if I'm making people disgusted. But anyway, if you have half a worm, so if you have half of 100 crossings, then on each half you'd have about 50 crossings. And then computing this would take 2 to the 50 operations. Computing this would take 2 to the 50 operations. 2 to the 50 plus 2 to the 50 is a lot less than 2 to the 100. Now, that's, so you can save by cutting in half. And in fact, after you've saved some by cutting in half, you can cut each half into a half, and you'll save even more. And that was essentially what we did last time. We actually chopped it into pieces of size 1. Okay? But there are two issues. One issue is, well, we first have to understand what is the Kaufman bracket of half a knot. Okay? And the second issue is, and the second issue is that once we understand it, there is a cost for gluing the results. So I lied when I said that the cost of computing is 2 to the 50 plus 2 to the 50, because you have to compute the left-hand side, you have to compute the right-hand side, and then you have to pay the price, whatever it costs, to glue. And we have to understand that cost too, and that cost is what's summarized in the formula above. Okay? So that's the general context. Now, okay. So I have to tell you a little bit about half knots in half apples, right? But even before that, let me say that the result, whatever it is not going to be one of the algebraic structures that you know. Because if you're looking at an algebra, say, or a group or a ring, you end up multiplying elements in order, right? You end up multiplying elements in order, A, B, C, D, E, da, 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 okay? Now, like if it's non-commutative, then the order matters. If it's commutative, the order doesn't matter. But whatever it is, you multiply in order. But if you're talking about pieces of a knot, sort of, you need to be thinking about multiplying in a plane. So this piece is to the right of that piece, but that piece is above it, and that piece is above. Basically, you can multiply both going left to right and going up down. So it's a different sort of algebraic structure that you will have to manage. Okay? Good. So what's a tangle? So definition, a tangle is, so it's essentially half a knot or half a worm in half an apple, or said differently, it's a disk. So the disk comes to indicate a part of the plane. So instead of being a knot diagram on the whole plane, it's a knot diagram on a part of the plane. That part of so that disk has a number of points on its boundary. These are the points that are going to be like the interface points. That's where the strands come in and out. In addition, there are strands. So the strands are just a part of a knot diagram. So say you'd have a strand going from here to here, another one from here to here, but going under that one, another one going under that one, then under that one, then under that one, then under that one, then maybe over that one. The problem is that I'll have, I don't know how to indicate over, I'll just cross it over, and then going that way, and then the last one going that way. And perhaps in addition, you'll have components that do not even touch the boundary. So somewhere inside you may have a component that looks like a trefoil knot. Okay? So that's a tangle. And then you mod it out by the same Reidemeister moves as before. So by Reidemeister 1 and by Reidemeister 2 and Reidemeister 3, they all make sense in this context. Now, different people have different notions of what a tangle means. So some people will do the same, but will insist that instead of being in a circle, it will be in a square, and the distinction is that in a square there will be, and that all the boundary components will be either at the bottom or at the top. So in a square there will be a top boundary and a bottom boundary. Some people will insist that there are no independent components, no components that do not touch the boundary. Okay? And I think the main thing I want to say is that I don't want anybody to insist on anything. That's the whole point of all on beyond zebra, right? There is the type that goes this way and the type that goes that way, and there are slightly different things to say about them, but you shouldn't insist on any. So for today, this is my definition. Okay? Maybe I should add all of the strands should be directed, so there should be an arrow telling you in which direction to flow on each strand. And furthermore, there is some base point on the circle. So basically you cannot rotate the circle because there is an indicated point here, which basically all it does is it says that this is the, like if you go counterclockwise, it means that you can number the ends. So 1, 2, 3, 4, I don't know, I forgot the rest of the count. Okay? Good. Now, how can you compose tangles? By the way, so far, knots were isolated objects, each knot to itself. Okay? And from the perspective of algebra, that's not very interesting. Things get more interesting once you have operations. So once you can compose knots or act on them in various ways. So all at once, the moment I start talking about tangles, things get more interesting because you can compose tangles, and from smaller ones you can get bigger ones. Okay? So anyway, how can you compose tangles? So suppose you have 3 tangles. You know, maybe I'll distinguish the external circle of a tangle by making it black. And here are my three tangles. So the first one is this one, the second one is that one, and the third one is, say, that one. I chose all three tangles to have just one crossings. One crossing in each. Of course, I could have chosen something more complicated. Okay? So how do I compose such three disks? So one way to do it is to, well, draw a larger disk around, and the larger disk will come with instructions, and the instructions say stitch this to this, stitch this to this, stitch this to this, and then all the remaining legs will go to the outside. So the composition operation, right? So the inputs were these three tangles. I could have put inside these disks here, these holes, I could have put different tangles. I could have applied the same kind of composition operation just as well if I had here, instead of the tangle now drawn, so let me delete it, and instead draw another one, I don't know, this one. Okay? I could have applied the same composition operation even if the tangles themselves were different. So what was the composition? What was the thing that played the role of multiplication? So it was the diagram sandwiched between the external circle and the three internal circles, and that diagram is just four circles in our case with a bunch of green lines in between. So that diagram in our case was this diagram. If it looks a little bit like a face, it's a coincidence. So in our case it was this diagram. Okay? Now every such diagram is an operation on tangles. Right? Every such diagram, so every diagram which has an outer disk and a bunch of inner disks that have and a bunch of connections between them is an operation on tangles. It's like a multiplication operation for tangles, because you can plug three inputs into such a diagram inside the inside disks, and the result will be a bigger tangle that you read basically if you erase the black lines, if you erase the input black lines. Okay? And I lied a tiny bit, and the tiny bit of a lie is that if I tell you plug this tangle into this hole, there is a little bit of an ambiguity of you can turn it around, right? So this hole, so just as I said that tangles should have a base point, these holes should also have a base point, which would specify, basically you would have to plug any tangle into this hole so that the base points match. And since I want the output to be of the same type, then the output should also have a base point marked somewhere. And it somewhat depends on how pedantic you are, oh, wait. Yeah, I was going to say you may want to orient these lines as well, but now it occurred to me that I actually made a mistake. namely, when talking about the Kaufman bracket, in the Kaufman bracket orientation doesn't matter. When I first drew the Kaufman relation, I didn't even bother to indicate orientation. So sorry, my tangles for today are unoriented, no orientations, and therefore the operations between them also don't need to have those extra orientations. So I suppose there are two types of planar algebras, the oriented ones and the unoriented ones, and today we need the unoriented ones. Okay.
Question.
Yeah.
So with the red dots, does one choose where to position them, or they should be fixed at the pointing in some direction?
They don't need to be fixed. So they are a part of the information that appears in an operation. Okay? Good. But alternatively, I could tell you that all of this should be regarded as combinatorial objects, not as geometric objects. So, in other words, this picture is for me equivalent to the picture that you would that I would get if I would erase one of these green lines, and instead of writing it the way it was from here to here, I'd write it from here to here. Okay, so all of these pictures are regarded as combinatorial. So in the same way, so basically differing things that differ just by a diffeomorphism of the plane, by an automorphism of the plane, are the same. So in the same way, I could move this red dot from where it is to say here. So these two are the same. But if I'll move it past the end of a green line, then now this is a different combinatorial structure. It's a graph. So these are not the same. Okay? And by the way, since the word not is the same word as the word for a knot, I will sometimes use the Danish. So these are ikke same. Okay? Ikke means not. Good. But now let's turn it into a formal definition. Okay? So definition, what is definition, sorry, in blue, definition, a planar algebra is. So what is what goes into a planar algebra? Okay, so so there is a space of tangles. Okay, so I mean planar algebras do not need to be about tangles. Okay, but the one example we have is tangles, but we have tangles with each number of legs. So if you have tangles with 0 external legs coming out, with 1, with 2, with 3, right? In our pictures, these all are tangles with 4 legs coming out, but the output tangles that you get after you multiply is a tangle with 6 legs coming out. So in a general planar algebra, I will want a collection Pn of sets of objects. So where in the example P0 will be tangles with 0 legs, P1 will be tangles with 1 leg. How many tangles are there with 1 leg?
None?
None.
Okay.
Because you cannot have, because tangles will have to have an even number of legs. Okay? So, I mean, in the case of tangles, P1 is equal to 0, but in general, I'm not insisting that it's empty, sorry. So then P2 is tangles with 2 logs, and so on. So it's a collection of sets of objects. And again, in many algebraic structures, so, you know, a group has just one type of objects. But a vector space has 2 types of objects, like a field element, scalars and vectors. So a planar algebra has infinitely many types of objects. One type for each number of legs. Okay? So it's a collection of sets of objects plus a collection of operations, and the operations are labeled, so one operation for each, so labeled by so-called planar connection diagrams. So again, in many spaces you have more than one operation, right? In a vector space you have addition and multiplication. No, that's not in a vector space, that's in a ring. Okay, whatever. So for a planar algebra you have many operations, and these operations are labeled by planar connections diagram. What's a planar connection diagram? A planar connection diagram is I suppose a Swiss cheese kind of object. So it's a disk with several disks removed, with green lines connecting those various disks. These green lines must be planar, non-intersecting. That's the planar in the definition. With red dots, so red dots on each of the disks. And one additional little property, which is that the input disks must be numbered. So let's say this one is numbered 1 and this one is numbered 2. And then what is the operation corresponding to such a disk? So this disk is an operation from P4, because there are 4 legs on number 1, cross, here there are 1, 2, 3, 4, 5, so cross P5, with output in P 1, 2, 3, 4, 5. In this case, P5. In general, every planar connection diagram will correspond to an operation with multiple inputs and one output, and you can determine the subscripts by counting the red lines. Sorry, the green lines. Okay? And yeah?
So you mentioned the planar requirement that the pairings have to respect some planar embedding.
Yeah.
Do we require that the points along these boundary circles be all oriented, say, counterclockwise?
So the moment you chose the red, yes. So the moment you chose the red dot, it means that you can enumerate these points.
All right, and we choose the same orientation for the inner circles as for the outer circle.
Yes, but I don't need to draw the orientation because you can read it off the. I mean, it's just counterclockwise. Okay.
Okay.
Okay. There's no.
Sorry.
Yeah.
Mind if I ask a question? So the idea is that you you have you have a disk with like four strands or like 4 points on the end and a disk with 5 points on the end, and then you put them like into the thing you just drew?
So I gave one example so far of a planar algebra.
Okay. Okay.
Okay, and that example was tangles.
Right. Okay.
Okay, but in that example, the objects are themselves disks with tangles written in them, and you can plug them in. And the
Okay.
operation is to plug it in.
Okay.
Okay, but there will be other examples
Right. Okay.
in which the operation might be something else. But nevertheless, I insist that that will be the collection of operations.
Okay.
By the way, I could drop the requirement of planarity. So if I allow the green lines to intersect, I also get one of those things in this beyond zebra world. So these would be circuit algebras. But at the moment we don't need them, so we're not going to talk about them. Okay?
Wait, are the green lines, like, do they have to be going from disks to other disks, or can they go from disks to, like, the same disk?
Oh, yep, you are right. I should have allowed that too. But now that I've added another green line, or not allowed, I never said it's not allowed, but sort of, I should have given it as a part of the example. But now the input now is not P5, but P7. Excellent. Okay? Good. Next, but then there is one axiom, right? The group, there is some associative law. So, in a planar algebra, there is also an axiom. And the axiom is a bit hard to state, so instead of stating it in full, I will give an example. Okay? So, here is well, here is an amusing picture. Okay? Okay? So, you can look at this picture in three ways. Okay, you can look at this picture in three ways. Let me take one of the circles. So let me take this circle and call it, what should I call it? I don't, it really doesn't matter. S for special. Okay? So you can look at this picture as a planar algebra, as a planar connection diagram in three ways. You can remove S. So if you remove S, then the operation that remains is an operation. So again, let me now number, you know what, let me not number, let me just say that I will number from left to right, okay? So if you remove S, the operation so this S doesn't appear, so now you're left with three input circles and one output circle. So this is an operation from P4 cross P4 cross P3 into P3. Okay? You can remove the outside of S, so you can remove the outside of S. So basically everything outside of S gets removed, and you're left with just this thing here, the thing that's inside S. the thing that's inside S is an operation from P4 cross P3 into P3. Or you can remove the inside of F. So remove the inside of S. So if you remove the inside, you're left, so S itself becomes an input, and you're left with an operation from P4 cross P3 into P3. And the condition is that these operations are compatible. And what does it mean to be compatible? It means that if you take, so basically the first one is equal to the composition of the second two. So if you take any element of P4 and another one of P4 and another one of P3, so let me give these elements names. So let me call them A, B, and C. And in fact, let me give, so really A corresponds to what sits here, B corresponds to what sits here, and C corresponds to what sits there. And in fact, why don't I give names to the operations as well? So let's call this operation phi, this operation lambda, sorry, I wrote phi again, lambda, and this operation mu. So the compatibility condition is that if you compute the overall operation to A, B, C at once, in other words, if you compute phi of A, B, and C, then it should be equal to, so I could have first composed B and C. So that would be using the lambda operation. So I could have computed lambda of B and C and fed it into, along with A, into mu. So I'll get this thing. Okay, so I first compute the first composition and then the outside composition. So this is the compatibility condition. Okay? Now, this compatibility condition is, of course, I drew it on an example, but I meant whenever. So whenever you have a diagram, a Swiss cheese diagram with an additional circle S, you can draw such a picture. You can set up such a situation. So I think it's clear, and it's clear that tangles satisfy it. So in fact, maybe the next thing is to give examples. So example, tangles. I have nothing to say. They have everything you need. In the case of tangle, Pn will be tangles with n inputs, and as it turns out, P of any odd number is the empty set. Let's do another example. Are people familiar with tensor product of vector spaces? Okay. So example number 2. So example number 2. Let V be a finite dimensional, and it's important that it is finite dimensional vector space. with an inner product, product, okay? And let Pn be the nth tensor power of the vector space. Except I want to think of the element of Pn. So, okay, sorry, so this is V tensor V n times. And I want to think of the elements of Pn in the following way. So, in general, an element of V tensor, so V tensor V n times is the set of linear combinations. So, in fact, maybe I should not have used round brackets, but triangular brackets. So this is the space of linear combinations of things of the form A tensor B. No, let's make it A1 tensor A2. You know what? Sorry, I'm taking it back. So, sorry, I take it back. Let's write it as V1 tensor V2 tensor V3 and so on up to tensor Vn, where each of these are, so where each Vi is an element of the vector space. Okay? And the way I want to visualize it is by drawing it inside a circle. So if I have a circle with a beginning point here, then I will draw the V's in order. So V1, V2, V3, and so on, up to Vn around the circle. So this is somehow how V tensor to the n corresponds to disks with some marking on them. Okay? And now I need to tell you how the composition operation works. So the composition operation is tensor contraction. If you've ever seen contraction of tensors, that's it. Namely, so suppose I have an operation so here is an operation, and suppose I feed it, actually sorry, to be an operation I still need to add the red marks, and suppose I feed it with elements. So I need to tell you how the operation acts. So suppose I feed this operation with, this disk, I put into this disk an element of P4. An element of P4 is a tensor product of 4 vectors. You know what? Let me delete one of the lines to make it not both the same. Okay? So, so an element of P4 is a tensor product of 4 vectors. So let's call them V1, V2, V3, and V4. And similarly, let me feed here an element of P3. So it will be W1, W2, and W3. And then applying the operation will give me, so the rule will be that any 2 vectors that are connected by a green line, I contract, which means I compute their inner product. So the output will be, I made this circle too big, the output will be the inner product of V2 with W2 times the inner product of V1 with W3. All of this multiplying, well, in a tensor product I allow linear combination, so I'm multiplying this with with what remains. So what remains is a circle with 3 things marked on it, and those 3 things are W1, V3, and V4. And you're welcome to check that all axioms are satisfied. Okay?
Since we're
Question.
not doing first, no.
Yeah, sorry, Hireng, yeah? What were you saying?
Oh, I'm sorry. I didn't know my mic was on, but I do have a question. If we enforce planarity here, doesn't this restrict which vectors can be
Yeah.
inner
So
products?
in fact, this planar algebra. So in fact, the case of V tensor to the n is in fact a circuit algebra, but a circuit algebra is in particular a planar algebra. So here I had more operations. So when you're talking about contractions of tensors, you have more operations than merely the planar ones. Okay, but I just wanted to give, here is another example of it's in particular a planar algebra. Right, what you're saying is essentially like saying, you know, I'm telling you that the real numbers are a group under addition, but then you're saying, but you can also multiply. Of course, you're right. So you can do more operations as well. Okay?
Yeah.
So,
A question.
and by the way, here, the picture sort of, I mean, it's not obviously the same thing as tangles. It's not tangles. It looks completely different. Yes, Leonard?
Yeah, so up above you had a P of an odd number to be equal to the empty set.
Yeah. This is in the previous
So
example.
I was expecting this one to also be empty. We shouldn't have
No,
anything
here-
here three lines coming.
Here P3 is not empty. P3 is the third tensor power of a vector space. It's not empty. So it doesn't have to be that odd P's are empty. Well, I only have 2 minutes left or so. Oops, why did I do undo? Sorry, I wanted to do, sorry, I wanted to hit something else and I hit undo. So, I need to give you one more example. And the last example is the Temperley Lieb planar algebra. And since I don't have time, I'll do it very, very, very quickly. So Pn, or you know what, let me just give an example. So P6 will be the span, so the set of all linear combinations of circles, so it's a bit like tangles, with the difference that now the tangles are themselves planar, are themselves planar. So the insides are not allowed to have intersections. So basically, these will be pictures like this, or a similar picture would be I don't know, this one, or well, there are other pictures. Okay, so the tangles, so it's again sort of a planar algebra of tangles, but the tangles have no crossings. And I will make an additional, I will insist on an additional relation. And the additional relation is, well, so you see, when you compose two such things, when you put two such things next to each other, a circle might be created. right? If I connect this to this, sorry, that's not what I wanted to do. Well, if in some ways of connecting, I may end up creating a circle. So I have to mod out by a relation that says that you can delete a circle and replace it by a factor d. Okay? Where, you know, if you insist, I could... Okay, so this is a planar algebra over the ring of polynomials in the variable d. And in fact, I could have made it the span over the ring of polynomials in A inverse, and I could have declared d to be negative a squared, negative a to the negative, whatever it is in the Jones polynomial, and I'll get a planar algebra over Laurent polynomials in the variable a. So so this is the temporally-lib planar algebra. And then, and sorry, now I'm a minute over time, but I will take another 20 seconds just to say that now at least the two declarations that I made in the beginning make sense. The Kaufman bracket is a morphism of planar algebras. I didn't yet define a morphism of planar algebras, but it's the same as a morphism of any two algebraic objects. And the second statement is that the rank of temporally lib 2n is given here. Okay, so I'm afraid I have to stop. So see you on Monday. Questions, comments?
I've got a question about the tensor products.
Yeah.
Planar algebra.
Yeah.
Does it, in our example, because the lines are unoriented, do we have to use a real vector space? Because we need to worry about the difference between the inner product W.
Yeah, you're right. So I need a symmetric inner product. So it has to be a real vector space. There is a notion of an oriented planar algebra, and in an oriented planar algebra, in fact, you don't even need an inner product, because what you can do is you can put V on incoming lines and V dual on outgoing lines, and then there is an evaluation built in. You don't even need an inner product.
Okay. Thanks.
Other questions? By the way, it is useful. These planar algebras are all used in various places.
Are we going to talk about how they are used elsewhere, or I guess we can bridge it up somehow?
No, but we're going to talk about even more bizarre planar algebras later on. But not, well, you know what, the truth is that I haven't entirely decided in which order to go over things. It partially depends on your interest. My plan is, when this is done, to go to Chovanov homology, and in Chovanov homology, all of this is relevant except it's more complicated.
Well, I like homology, so I vote for that one first.
Well, but that's already decided, so the question is what's after. Okay, see you all on Monday.
Sorry, can I ask a quick question?
Let me stop. Oh, you know what? I'll keep the video if it's a math question, but class is formally over. Yes.
Yeah, so it's a question of the flavor of like contextualizing the sorts of things that you've defined. So say I were to like define some algebraic structure that's similar to this, but without these strands. So I'm just defining some operation where I take like some disks with some disks removed, and I have n area operations where I glue these in to remove disks of larger disks. Then this is the sort of structure that I would expect from like the observables of a 2D TQFT. So should I like what's the right context of that flavor, that the sort of thing that you've defined should show up in? Like should I expect that like I'm like including some possible like line defects, and I can insert operators like along the line defects or something?
So you're clearly using a very physical language.
Yeah, I'm half a physicist, I guess.
So, yeah, I don't want to commit myself to the same language. So, but yes, this is related to TQFTs, where you know, TQFTs or two-dimensional TQFTs are the same but without the lines.
Yeah, exactly.
But not quite the same, because it doesn't have to be a disk, it can have a higher genus. So the things are related, but I'm
The thing
not
attached
sure.
to S1 will have exactly this structure without the lines, right?
Sorry, the thing at.
Like if you like to think of TQFT, I don't know, functorially or something, the thing that's attached to S1 will have exactly the sort of structure you're talking about, but without the lines?
Well, no, because you usually are talking also about higher genus surfaces, not just disks. So instead of disks with holes, you will be talking about a higher genus surface with holes. Right? You could be talking about, you know, your operations could consist of, well, a pair of pants is just a disk.
Yeah.
But instead of a pair of pants, you could have been talking about a pair of pants with a hole.
Right.
Okay, you could talk about things of higher genus. And that will be closer to a TQFT. To a TQFT, right, but... So
But
so we are talking about genus 0 TQFTs, or TQFTs restricted to genus 0, if you wish.
Okay.
Okay? I'm not sure what else to say.
Okay, thank you.
Okay. Other questions or comments? Yay! I'm going on vacation for the weekend. See you on Monday. Bye.